Okay, here we go. Went ahead and did a little work here just to follow up on our shear moment diagram reactions, calculations, and shapes. Wanted to do one a little beyond what we've done in the past, and let me walk through what I've done here. Again, we've got a uniformly varying load. As you'll notice up here, it is going from 0 here up to an intensity of 12 kilonewtons per meter, and then back down to 0. We have, again, a simply supported beam. What we do is determine the shear and moment values and diagrams, of course, looking for the maximum moment values and the maximum shear values. And basically what I did, I went through and calculated the reactions as follows. Notice these are triangular shapes, and so the area is nothing more than the base, which is 1.5, times the height, which is 12, divided by 2, and that number is 9. On this side, it's a half times 12 is 6, divided by 2 is 3, so our total load is 12 kilonewtons for the whole beam. Then what we do is, as we've done in the past, is we'll sum the moments about the left side, which is right here, to determine that the reaction on the right side is 7.01 by summing moments about the left. Notice the 9 and the 3 act at centroids. So recalling from statics that the centroid of this side is 2/3 of 1.5, which is 1 meter. And on the other side, from the apex to the centroid is 1/3 of 0.5, which is 0.17. So summing moments about the left says it's 1.5 plus 0.17, so that's 1.67 feet from the left-hand reaction. Summing the moments gives us a reaction at the right of 7.01 kilonewtons. Well, if we subtract that from 12 kilonewtons total, we get, subtracting that, we get 4.99 kilonewtons for the reaction at the left. And that looks pretty good. We think that'll work okay. Well, let's see now. Let's see if we can get the shape of this thing. And recalling, and I'll sketch it before we do any calculations, and it looks like this. We know that the shear is increasing from left to right. But we also know from our equation, and we're going to write that here in just a second, we know that this jumps up because the reaction is up, 4.99. We also know that those arrows are down and the slope is increasing. So we know it's going to do something like this. Slope is increasing, increasing, increasing to this point. Oh, had a little problem there. Let me try it again. To this point. But we also know from the apex over to the right it is decreasing. So we know we have an inflection point here, and it's going to do something like this. That's a little radical, but that's what it looks like. Now, we also know that, now this is our shear diagram. We also know that our moment diagram is a mirror image, in many cases, of our deflection shape, of our elastic curve. So we sort of know that the moment diagram, let me see if I can find another color here. There's one right there. The moment diagram is going to, recalling this is area 1, and this guy down here is area 2. It's going to, and we know it has to climb on this side and dive on this side because the areas are plus and minus respectively. Also notice that the load, correction, the shear is decreasing, so we know it's climbing but it is decreasing. It's going to look something like this. Now over here, it is increasing from left to right, even though it's negative, so it's going to look something like this. The question is, we need to know where that point is, simply because that is the point of maximum moment, and it's not necessarily where the apex is as we calculated. So we're going to do a little work here and determine those values. Again, we're looking for area 1 and area 2, and we also notice that area 1 has to be equal to area 2 because the moment at the endpoints, the supports is 0 here and here. So what we want to do is, and recall, when we integrate the load, we get the shear. And when we integrate the shear, we get the moment. Well, let's see if we can make that work. We know that this load over here, this shear value, is 4.99. We also know that the general equation for that triangle from left to right looks something like this. So let's take a look at the shear value first. The shear equation, shear is going to look like 4.99 is plus, and he's up, minus the area over here down as we travel from left to right, and that is going to look something like this. We know the slope of this line up here is 12, rise over the run is 12 over 1.5, so that looks like 8. Well, it looks like this. It looks like 8 times x squared divided by 2. You'll note that that is the area of the triangle. It may not be intuitively obvious right at the minute, but the area of this triangle as we move from left to right is the rise, or I should say the slope, times x is the height. X is the base divided by 2. So that equals our shear value. Well, the beauty of this is all we have to do is set the shear equal to 0, which will give us that distance right there. And we know it's a parabolic shape. There's our squared. There's our parabolic shape. We know we are literally in good shape to solve that equation for x. Well, quadratics, if you'll recall, there's a number of ways we can solve quadratics, but solving for x then equals 1.12 meters. So that distance right there is 1.12 meters. And we can put that equation in, that number in there, and see if it tracks, but I know it does. Well, now, recalling that if we integrate the shear, we get the moment. Well, all we need to do is integrate that equation, the shear equation, and let's write that we're going to integrate 4.99 minus 8x squared over 2 dx looks something like this. 4.99 times x minus 8x cubed over 6. We're going to integrate that from 0 to 1.12, we will discover that that turns out to be about 3.73 kilonewton meters and checking units approximately equals 2,236 foot-pounds. Now, the exercise again is given that shape because that comes from some wind loadings, come from hydrostatic loadings, and you'll see when we get to concrete formwork that we're going to see those hydrostatic loads on a continuing basis. So our Vmax, if we look at this number, looks to me like from our equation, here's 4.99 or 4.99 on one side, looks like about almost 5 kilonewtons. Over on the right side looks like approximately 7 kilonewtons. We look at our maximum moment, looks to be about 3.73 kilonewton meters, or about 2,236 foot-pounds of moment. So hopefully as we progress, that will allow you to have a better understanding of uniformly varying loads, how to go about solving for, oddly enough, there are those integrals that you used in Calc 1, 2, and 3 showing up again, and a little bit of algebra in solving the quadratic equation. And recall that is minus b plus or minus the square root of b squared minus 4ac over 2a. Of course, you all remember that, or you can use those snazzy TI calculators and figure that out. Or you can complete the square, trial by fire, trial by error, whatever you'd like. All right, and let's check my math, please. Make sure I got the right conversions. Make sure I did my math right down here, that I integrated these equations correctly, and I got the right SIGNs on the various components of the equation. Good luck.